welcome to the deep dive. Today, we're embarking on a pretty epic journey that spans millennia, really.
It really does.
We're tracing the lineage from these ancient dreams of artificial life all the way to the massive, complex neural networks that are basically running the world today.
Right.
And our mission here is to trace that complete history of the computer, of artificial intelligence, to really understand how we ended up in this AI-powered reality.
It's a fascinating path to follow. And what stands out, right away is that the evolution of computer science isn't some straight technological line.
No, not at all.
It's more of a convergence point. You have this fusion of rigorous mathematical theory, pure mechanical ingenuity, and sometimes just, audacious human ambition.
I like that. Audacious.
The pattern is striking. You see visionaries consistently imagining intelligent machines long, long before the physics or electronics existed to actually build them.
And that ambition is our guide today. To map this journey for you, we're going to cover a few critical stages. First, the foundational concepts, starting with myths and formal logic.
The very beginning.
Then we'll get into the mechanical and electronic breakthroughs that built the actual hardware. After that, the official birth of AI at Dartmouth in 1956. And, of course, the AI winters that followed.
The boom and bust cycles.
Exactly. And finally, the modern resurgence of deep learning and its powerful and very complex implications for all of us.
Sounds like a plan.
So let's unpack this, starting way back in antiquity, where the very idea of an artificial life first took hold.
That vision it's so deeply rooted in human history. You find it in myths, like the myth of Talos.
Oh, the bronze giant.
The giant bronze automaton, yeah. Crafted by a god, Hephaestus, to protect the island of Crete, a tireless, self-moving guardian. Or you have the golem in Jewish folklore, a figure animated by mystical rituals.
So these were sort of the conceptual placeholders for non-human intelligence.
That's a great way to put it.
Yeah, but the concept moved pretty quickly from myth into actual engineering, right? Centuries ago, we start seeing these real mechanical marvels.
We do. Think of the Chinese engineer Yan Shi, who allegedly presented a king with this life-sized humanoid figure that could walk and sing.
Unbelievable. And what about in the West?
Well, you have Hero of Alexandria, who was designing these incredible self-operating machines, theatrical automata, powered by steam and water pressure.
And then even later, Al-Jazari.
Oh, absolutely. In the medieval period, Al-Jazari crafted these genuinely sophisticated, programmable automatons, musical robots that were, huge attractions in courtly settings.
So they were basically demonstrating very early programmable mechanics.
Exactly, but those were impressive clockwork. For computation to truly advance, it needed something more than gears and levers.
It needed a language,
Yeah.
a formal theoretical language.
Precisely. The breakthrough wasn't in the hardware, it was in the intellectual frameworks. We have to look back to Aristotle, who formalized syllogistic logic, just establishing the structure of valid reasoning.
And Euclid with his proofs.
Right, systematizing mathematical proofs, creating algorithms for geometry, and of course, Al-Khwarizmi, who gave us the step-by-step procedures that gave us the very word algorithm.
Okay, but the real hinge moment, the thing that connects philosophy to the future of digital hardware, that happens much later with mathematical logic.
George Boole, 1854.
What he did was phenomenal. He reduced all of human reasoning, all logical propositions, down to simple binary operations.
True or false, 1 or 0.
That system of Boolean logic was just. It was incredibly powerful. It meant complex thought could be reduced to a simple series of switches.
And that became the fundamental language that every single digital computer speaks.
But that language needed a theoretical machine to run on.
And that brings us to Alan Turing in 1936.
Everyone cites Turing's abstract machine, but what did it actually prove? Why was it so important?
It was a proof of concept, a thought experiment. Imagine the simplest possible mechanism, an infinitely long tape, a head that can read or write symbols, and a finite set of rules. Turing proved that this simple device, the Turing machine, could perform any computation that any other computer could ever execute. He basically established the fundamental boundaries of what is even possible with computation.
All before the first electronic computer was even built.
Exactly, the ultimate foundation for the entire field.
So once that theoretical groundwork was laid by people like Boole and Turing, the race was on to actually build the physical machines.
Right, and the early attempts were mechanical. You go back to the 17th century, and Gottfried Wilhelm Leibniz designed the stepped reckoner.
Which was basically a fancy calculator.
A very fancy calculator, yeah. It could do all four arithmetic operations, multiplication, division, not just adding.
But the true precursor to the computers we know came from Charles Babbage in the 1830s. His plans for the analytical engine they were just revolutionary.
They really were. Babbage essentially described the architecture of a computer we would recognize today. He designed it with a separate mill,
The processing unit.
the processing unit, yeah, and a store, which is basically memory. He used punch cards for input, for programming, and most critically, it could branch. It could make decisions based on conditions.
So it wasn't just a calculator. It was a programmable machine. A full century before it could be properly built.
A full century. And his use of punch cards came straight from industry, didn't it?
It did. Babbage borrowed that idea directly from Joseph Marie Jacquard's automated loom from 1804.
Jacquard used these stiff cards with patterns of holes to automatically control the weaving of these really intricate designs.
So that showed engineers that instructions could be stored separately and changed easily.
Which was a huge influence. Then comes the massive paradigm shift in the 1940s. We move beyond gears to electronics. You see Konrad Zeuss's Z3 in Germany in 1941.
Generally seen as the first working, programmable, fully automatic digital computer.
Then the Atanasoff-Berry computer at the ABC, which introduced vacuum tubes for computation.
And those vacuum tubes were the secret sauce.
They were everything. They allowed computation to happen at the speed of light, not the speed of turning gears. And this all culminated in these behemoths like ENIAC at the University of Pennsylvania in 1945.
Which could do something like 5,000 operations per second. Just unheard of speed.
But speed was one thing. The real architectural breakthrough was the ability to change the program without physically rewiring the entire machine.
That's the key transition. Early systems like ENIAC were fast, but you had to physically rewire them for every new problem.
Exactly. The huge organizational leap, influenced heavily by John von Neumann, was the stored program concept. The idea that the instructions, the program, are stored in the same memory as the data.
And that's what made computers truly flexible. It moved them from specialized calculators to general-purpose information processors.
Which is the definition of a modern computer.
That flexibility set the stage for the next big intellectual leap, artificial intelligence. And that's marked by one specific event.
The Dartmouth Conference, summer of 1956.
Right. This is where the term artificial intelligence is officially coined by John McCarthy.
It was a heady, ambitious time. I mean, the brilliant minds gathered there genuinely believed that machines could soon simulate every single facet of human reasoning.
They weren't thinking about narrow tasks. They were thinking about replicating the human mind.
The whole thing.
And the early results were promising enough to fuel that excitement. We saw Christopher Strachey's Checkers program very early on, 1951.
But the true machine learning breakthrough came a bit later with Arthur Samuel's IBM Checkers program.
Because it could learn, right?
It learned. It didn't just play using fixed rules. It was designed to learn from its mistakes. It would adjust its strategy based on experience. That ability to improve over time without explicit reprogramming, that's the core of machine learning.
So as the field matured, the focus shifted toward pattern recognition. Which brings us to Frank Rosenblatt's perceptron.
The perceptron model in the late 50s and 60s was so important conceptually because it was directly inspired by biological neurons.
So it processed inputs, adjusted connection strengths or weights between nodes, and produced an output.
Exactly. It showed that these simple, interconnected structures could learn to classify data. It was a foundational precursor to the deep learning systems we rely on today.
That excitement carried on into the 70s and 80s, leading to AI's first major commercial success.
Expert systems.
The first time AI really made money.
These were the early industry champions of AI. They worked because they were designed to replicate the decision-making of a human expert in a very specific, narrow domain.
They didn't try to solve general intelligence. They focused on codifying rules for one subject.
The classic example is MYCIN, developed at Stanford. It diagnosed bacterial infections.
And recommended treatments, right, based on hundreds of if-then rules supplied by human doctors.
And what was remarkable was its performance. Studies showed MYCIN's diagnostic accuracy often matched or even exceeded that of human experts in the field.
So given that these expert systems were technically successful and commercially viable, why did that whole boom collapse?
That's where the story takes a harsh turn. We enter the first of the infamous AI winters.
Periods of dramatically reduced funding and interest.
The first big freeze descended in the mid-1970s, and it stemmed directly from overpromising combined with some devastating academic critique.
The nail in the coffin being delivered by Marvin Minsky and Seymour Papert.
Precisely. They published this analysis showing that simple, single-layer neural networks like the perceptron couldn't solve certain types of problems.
The famous XOR challenge. Can you break down what that is and why it was such a barrier?
Okay, so think of it this way. A single-layer perceptron can draw one straight line to separate two categories of data, like separating apples from oranges. That's a linear problem.
Easy enough.
But the XOR problem exclusive OR required the system to classify data that couldn't be separated by a single straight line. You need two lines or a curve.
And the perceptron couldn't do it.
Fundamentally incapable. Minsky and Papert proved it, and that effectively froze research into neural networks for decades until multi-layered architectures were developed.
And this academic disappointment was reinforced by political action.
Yes. The British government's Lighthill report in 1973 was scathing. It concluded human-like intelligence was unreachable, and that led to major budget cuts in the UK and the US.
And that ushered in the first long AI winter. But AI tried again with expert systems boom.
It did, but that led directly into the second AI winter in the late 1980s.
What failed that time? It wasn't a technical problem.
No, this failure was purely logistical and economic. Expert systems, while accurate, were brittle. The knowledge base required constant, expensive maintenance by highly paid human experts.
So as soon as the rules in the field changed, the whole system had to be painstakingly rebuilt.
Right. They just proved too expensive and too difficult to scale. So, commercial abandonment.
It's clear that technological progress rarely follows a straight line. What was the turning point that finally triggered the big resurgence?
The turning point in the 90s and early 2000s wasn't a new algorithm. It was a sudden abundance of two things: data and computational power.
The internet.
The explosion of the internet gave researchers massive data sets to train on. And at the same time, graphical processing units, GPUs, originally for video games, provided the massive parallel processing power needed to run these complex algorithms.
So suddenly, the deep neural network idea, which had been abandoned because of XOR, was practical again.
Exactly. That computational muscle led directly to the explosion of deep learning, starting around the 2010s. The innovation was using neural networks with multiple hidden layers, that's the deep part, which finally allowed them to solve those complex, nonlinear problems.
This is where we start hearing names like Geoffrey Hinton and Jan LeCun. Their work revolutionized things.
Hinton pioneered ways to efficiently pre-train these deep networks, and Jan LeCun was foundational in developing convolutional neural networks, or CNNs, which are specialized for processing images and video.
And that's why image recognition suddenly went from barely functional to having superhuman accuracy.
It forms the backbone of everything from self-driving cars to the Face ID on your phone.
Of course, the most decisive demonstration for the public was AlphaGo's 2016 victory over Lee Sedol in the game of Go.
That was the moment. Experts had always said Go, with its reliance on intuition and strategy, would be impossible for a computer to master.
And that victory just shifted the entire narrative.
It showed that modern AI could master intuitive strategy far beyond brute force calculation. It was intuition captured in code.
So as these incredibly powerful systems get integrated into every aspect of our lives, we have this escalating complex debate around the societal implications.
Absolutely. Algorithms are now influencing major life decisions, loan approvals, judicial sentencing.
Which leads straight to accountability. The immediate concern is the black box nature of these models.
Right. These networks have billions of parameters, and their sheer complexity means that often even their creators can't fully explain how a specific decision was reached.
So if an algorithm denies you a job, it can essentially say, "No, but I can't tell you exactly why."
And that's the conflict. That lack of transparency clashes with our principles of fairness and due process, especially in sensitive areas like justice or healthcare.
And all of these advanced models rely on massive amounts of training data, which just escalates privacy concerns.
Our personal information browsing habits, location data, facial images, it all feeds these algorithms, often with consent, that is. Well, it's vague at best.
You see this playing out with facial recognition technology in public spaces. There's this constant struggle to balance security against the erosion of anonymity.
And then, of course, there's the significant impact on the workforce. Automation powered by AI is rapidly replacing routine tasks.
And it's happening across the skill spectrum. We see manufacturing workers replaced by robots, drivers threatened by autonomous vehicles.
But critically, AI is now competing with white-collar and specialized knowledge workers. Administrative tasks are being absorbed by AI assistants, and even highly skilled roles like radiologists are facing disruption from these incredibly accurate analysis tools.
So what does this all mean for us now? We've traced this arc from ancient concepts through the logic of Boole and Turing, the genius of Babbage, the frustrating AI winters, and now to deep learning mastery.
Ah.
We are at a critical inflection point.
We really are. And the historical context is so crucial because it shows every advance has brought new challenges. The contemporary challenge isn't just building more powerful systems,
It's ensuring that technology serves humanity's best interests.
while rigorously respecting individual rights and societal values. The future outlook points to radical possibilities like quantum computing, but this absolutely necessitates the immediate and continuous evolution of ethical and governance frameworks for these systems.
So a final thought for you to carry forward as you continue exploring this convergence of innovation and responsibility. Charles Babbage conceived the analytical engine because he recognized the inherent limitations of manual human calculation.
He saw the fallibility.
Exactly. So the question is, what fundamental limitations of current human reasoning will the next generation of AI systems be designed to overcome? And when they succeed, how will those powerful systems change our very definition of intelligence itself? Keep exploring this remarkable story.